All right, so vectors. We've already seen vectors in extension 1, and that was all in 2 dimensions. The difference with extension 2 is we now look at 3 dimensions. So to start off with, let's look at this idea of moving from 2 dimensions to 3 dimensions. So in 2 dimensions, we know we've got our Cartesian plane, which we traditionally call the X and Y axes. And on it, we have one plane, but we divide up into 4 quadrants. The one where everything's positive is the first quadrant, and then we go around anti-clockwise. At any particular point can be defined with an ordered pair, an x-coordinate and a y-coordinate. That's what we're used to. So now what happens when we move to 3 dimensions? Instead of a Cartesian plane, we now have a Cartesian space. Here's the usual setup. It doesn't have to be, because you can rotate it and put it in any position you like. But this tends to be the standard way, and it might not necessarily be the way you were expecting. Imagine the XY plane, so what we call our Cartesian plane is flat. It's a flat surface. The positives are actually coming towards you with the x-axis here. And then coming up through the middle is now a third axis, the z-axis. So the arrows are pointing in the positive direction there. So there are now 3 axes, the x-axis, y-axis, and the z-axis. So we now have 3 coordinate planes. There is the xy plane, the xz plane, and the yz plane, which means we now break it up into 8 octants. We still start with the first one being where everything is positive. So in our picture, it's sort of like the one that's right at us at the front there. Then we move around, and then we move down. So they're the 8 octants. Don't panic too much about that. I don't think you're ever going to be asked, which octant is this point here, or something like that. And now points are an ordered triple instead of an ordered pair. So an x-coordinate, a y-coordinate, and a z-coordinate. Now when we deal with 3 dimensions, it's really hard to visualize it because we're using a flat piece of paper which is in 2 dimensions to represent a 3-dimensional thing. So sometimes we find it easier to actually draw in this rectangular prism there, and it gives it some sort of sense of where that point is in the plane. So often you'll see them do that to give you some sort of an idea. And OP, so the diagonal of that prism would be the, well, we'll come and see it in a sec, but it'll be the vector. All right, now in 2 dimensions, we know if we have a line parallel to the coordinate axis, well, if it's parallel to the x-axis, it would be y equals a constant number. Parallel to the y-axis, x equals a constant number. That's 2 dimensions. If we now have a point in 3 dimensions, and there's a plane parallel to the coordinate planes that goes through this point. So if I'm parallel to the xy plane, something like that, so every point on that plane will have a z value of 1. Because it's parallel to the xy plane. Parallel to the xz plane would be y equals a constant number. So on that green one there, any point there would have y value being 3. And then the third one would be when it's parallel to the yz plane, so the red one there, and that would be when x equals 2. There's similar sorts of ideas, but we're just pushing it through to a 3rd dimension. Some of the formulas that you're familiar with in 2 dimensions, what happens? So our distance formula in 2 dimensions, there it is, we're very familiar with it. What happens in 3 dimensions? So I want to find the distance between these 2 points. Again, to make life easier, I can draw in a rectangular prism there, and what I'm saying is, okay, I want to find the diagonal, the length of the diagonal of this prism. So I could draw in the, on the base, that line there, and I'll find that one first. But remember, that plane is parallel to the xy plane, so I could project that back down. And really, I could think of it now, oh, it's 2 dimensions now. I just want to find the length of the hypotenuse of that particular triangle. And the length of the sides would be the difference in the x value and the difference in the y value. It's our 2 dimensions. Well, the hypotenuse then is our distance formula, square root of x2 minus x1 squared, and so on. So we now know the length of well, Q, I haven't labelled it, but to the point straight under P there. So now using that triangle, I can do a distance formula. But look what happens. Because we're squaring it, because of Pythagoras' theorem, the square root and the square cancel, and we end up with something that's pretty much the same as 2 dimensions. It's just that now we're taking into account the difference in the z values as well. So we don't have to worry too much about how I got it. all we got to remember is, yeah, it's the same formula, but now I've got Z coordinates to worry about as well. Midpoint, similar sort of idea. You're finding the average of the values with a midpoint. So in 2 dimensions, you find the average of the X values and you find the average of the Y values. Well, in 3 dimensions, we do exactly the same thing, but now we also find the average of the Z values as well. So a lot of these things we already know in 2 dimensions transfer very nicely to 3 dimensions. Don't panic too much, because this topic is not a topic about 3-dimensional coordinate geometry. As much as I would love it to be, that's not actually in the course. This is a topic on vectors in 3D. So this is more just an introduction into thinking about 3D.